In this we can see one example for cyclic encoder, how we can encode the message as well as how we can draw the cyclic encoder. So we have the question: consider the 7 by 4 cyclic code generated by g of x equal to 1 plus x cube. The encoding circuit based on g of x is shown in figure 4.2. Suppose that the message u is equal to 1011 is to be encoded. So we need to encode the message 1011 using the generator polynomial g of x equal to 1 plus x cube. So our aim is to generate a systematic form of cyclic code. So that is generated using the generator polynomial 1 plus x cube. So now first we can see how we can draw the encoder circuit. So you should remember the general form of this encoder circuit as we studied earlier. So this is the general form of encoder of a cyclic code. So we already said how we can draw this circuit. So from this circuit we are going to draw our encoder circuit for given question. So we can see how we can draw this encoder circuit. So this represent the encoder circuit of our question. So in this we can see that our generator polynomial is 1 plus x cube. So that this we can see that after comparing it with the general equation of our generator polynomial, the general equation is g0 plus g1x plus g2x square plus g3 x cube. So here we can see that this g1 and g0 and g3 is 1, so that represent this g3 is represent this connection, as well as g1 represent this connection to this register. And from this next we can see that g1 is 1 here and g2 is, there is no coefficient for x square term, that means g2 is 0. So G1 equal to 1 means there is a short connection between this output of this register as well as this modulo 2 adder, and there is no adder needed for this second register output because G2 is 0. So based on that, whether it is 0, whether the coefficient of this generator polynomial is 0 and 1, based on that we can represent whether there is a need of adder, modulo 2 adder or not. So here there is no need of a second adder because this coefficient of G2 is 0, that means x square term is 0. So this way we can draw this encoder circuit. Next we can see how we can encode our message 1011. So our message is 1011, so the encoding will start from the LSB, that means the last bit 1101, that is the order of encoding of our message. And one more thing we can see that before doing this encoding process of our message, the first condition, that is the initial state of this registers are 0 0 0. So that is the initial state. First we need to clear all the content of this shift register, after that only we can give our input. So first the condition is 0 0 0. Then we are now we are turning on this gate. So after turning on this gate, we will give the input to this feedback circuit. So if we are giving first input 1, at the same time if we are giving the input, at the same time itself the content of this shift register will shift it out. So now the content is 0 0 0, so that will shifted to this point 0 0 and 0. So if we are giving the first LSB 1 to this circuit, that 1 and 0 modulo 2 added, and that result is given to this feedback. So 1 and 0 modulo 2 added means the output is 1, so that output will reach to this adder as well as this shift register. So the content of shift register is 1, and due to the first shift there is a 0 in this wire, so that 0 and 1 again modulo 2 added, so the result is 1, and that is entered into this shift register, and here there is a 0 that shifted to this shift register. So the content of this after first shift, the content becomes 1 1 0. So that is the content for this registers after first shift. Next we can see the second input, that is 1 again, so that time itself the content of this shift register shifted, so that this become, here become 1 and here become 1 and here become 0. and this 1 and 0 again modulo 2 added, and this 1 is given to this adder as well as this shift register. So this first shift register will get a 1, and there is already 1 is in this wire because due to the second shift, and this content of this shift register, this 1 and 1 will be modulo 2 added, and this modulo 2 addition give a 0, so the shift register is 0 now, and this there is a 1 that shifted to this shift register, so that becomes 1 for the last shift register. So now the content is 101 after second shift. Next we are giving the third input, that is 0, so this content of this shift register also shifted, so this last here this content now 1, and this 1 and 1, sorry, now the content of this shift register is 1, and this 1 and 0 is modulo 2 added, and it's again 1, and that 1 is given to this adder and this shift register. So the content of this shift register now become 1, and previous content is 1, and this 1 and 1 added, this shift register content becomes 0, and this previous case the shift register content is 0, that is given to this shift register. So now the content is 100 after third shift. Next we can see that we are giving the input 1, so this 1 at the time this point we have a 0 output, and the 0 and 1 modulo 2 added, again 1 and 1 becomes 1 and 1 will move to this adder as well as this shift register. So this shift register content is 1, and previous case there is a 1 and 1 added, so that becomes 0, and that 0 is given to this shift register, and the previous content of this shift register is 0, that will move to this shift register. So now the content is 100. So we can next we can see the step-by-step process of this encoding of cyclic code. So this is our encoder structure. First we need to initialize this flip-flop. These are the different flip-flop. These registers are called flip-flops. First we need to initialize this flip-flop. So the initialization is done by clearing all the content of this flip-flops, that is 0 is given to this flip-flop, so that is input. First is the initial state. Before giving this input we need to clear the content of this flip-flop. Next we can give the input. So first we are giving the input 1. Our message is 1011, so the LSB is 1. First we are giving that LSB. So at the time of giving this input, the flip-flop content will shift to this shift to the right place, one place. So this 0 will be now in this wire. So after getting this input, this 1 is modulo 2 added with this 0, so the result is 1. So that 1 will propagate to this wire, and the same one will also propagate to this flip-flop. So that after that calculating this so now after calculating the addition result of this modulo 2 adder, that is 1 plus 0, and that divided result is 1, that will given to this flip-flop, and when this content 0 is shifted to this place, so this 0 is shifted to this place. So this is the case when we give an input 1, that is the case after first shift. So next we can see what is the case after second shift. So this is now after giving this input we got this 110. So we given the second input 1. Our message is 1011. In that second bit we given a 1. So that time the content of the flip-flop will shift to right, that is 110 shifted to the right. Then using this 1 and 0, this modulo 2 adder add this 1 and 0, the output is 1, that given to this feedback path as well as this feedback path, so that 1 will get to this flip-flop, and using this previous 1 and this present 1, this modulo 2 adder will add, and the result 0 is shifted to this flip-flop. So at that time this 1 is shifted to this flip-flop. So this is the condition after the second shift. So the condition is 101 now. Then we can give the third input. Third input is 0. So this at the time this flip-flop content also shifted right. one place. So this 0 and 1 modulo 2 added, the result is again 1, that is given to this feedback as well as this flip-flop, the first flip-flop. Then using the result of the previous flip-flop content and the present one, this modulo 2 adder add, and the result is 0 is given to the second flip-flop, and the previous 0 of this second flip-flop is shifted to the first flip-flop, sorry, the third flip-flop. So this is the condition after third shift. Again we are giving the last input, that is 1. So the at the same time the present flip-flop content shifted one place, right? Then using this 1 and 0, the modulo 2 adder add this and we'll get the result as 1, and that is given to this wire as well as this shorted path as well as this flip-flop. And using the previous result of this previous content of the flip-flop as well as this one, the modulo 2 adder give a result of 0, and that's given to flip-flop 2. And the content of this flip-flop 2, previous content of flip-flop 2 is 0, that is shifted to this flip-flop 3. So this is the case after fourth shift. So again this is the flip-flop f of 1, f of 2, f of 3. So this is the content, our input, we given the complete input 1 0 1 1 at that time. This the shift after the fifth shift, this content of the flip-flop shifted right by one place, and that content is 1 0 0. Then by shifting this content, we can we will give this message together with this flip-flop content. This content is called as parity bit to the channel. So now the channel will get the complete code as parity bit followed by this message bit, because we already given this message bit, then this parity bit we collected, so that LSB, this message bit will be there, and then this parity bit. So our complete code vector is 1 0 0, then 1 0 1 1. So in polynomial we can represent it as 1 plus 0 into x plus 0 into x square plus 1 into x cube plus 0 into x raised to 4 plus 1 into x raised to 5 plus 1 into x raised to 6, that is 1 plus x cube plus x raised to 5 plus x raised to 6. That is the polynomial form of our code. So this way we can generate the systematic code. So we can see that in this first 3 bits, MSB bits represent the parity bit, and the last 4 bits represent the message bit. So we can differentiate where the parity bit and where the message bit. That's why it is called systematic code. So we can also realize some relationship between this flip-flop from this diagram. So we already said that this the input and this previous content of flip-flop 3 added here, and that is given to this flip-flop 1. So we can say that this flip-flop 1 content is f of 3 previous state plus this input, and this f of 2 is this f of 1 previous state plus this f of 1 present state, because this input plus this flip-flop previous 3 flip-flop 3 previous state is given to this wire as well as this f of 1. So this input plus previous f of 3 is the present f of 1. So we can say that this is the present f of 1 itself. That present f of 1 plus previous f of 1, if we added modulo 2 addition, we will get the f of 2. So we can write the f of 2 as f of 1 plus f of 1 previous, and similarly f of 3 is the previous of this f of 2. So this is the relation among different flip-flop. Using this relation you can easily write this expression without giving input and this sum to this, without giving the input and checking the condition of this flip-flop. Using this relation you can directly write down what is the conditions after initialization. So the first condition is initialization. So this is after first in this first shift we are giving the input 1. So at that time the state of flip-flops are 1 1 0. Then second shift we will give the second input, then 1 0 1. Then in the third shift the condition of flip-flop is 1 0 0, and the fourth shift again the condition is 1 0 0. So the fourth bit condition indicate the parity bit, and our complete code is 1 0 0 1 0 1 1. So this way we can realize an encoder in systematic form. So this is the encoder of cyclic code in systematic form. So in next class we can study the syndrome decoding of cyclic code.